friction, we say a gem cannot be polished without friction, nor a man perfected without trials. This is Lucius Seneca, who's a senator in ancient Rome. So, for this explain, what we're trying to figure out is to describe the effect of friction on net force. We want to be able to calculate and describe the direction of the frictional force. We want to be able to distinguish between kinetic and static friction, and also we want to know about the forces that affect a block on a ramp, both friction and otherwise. So, we know that friction opposes the motion of the object. Now that's a definition that we learned in a previous section, but we learned about it in detail in the experiment that we did. We said, okay, I have a really large, or I have a mass there, and that mass right there sometimes made this block move across the table and sometimes it doesn't. And it depended on kind of the surfaces that were here, but it also depended on the amount of mass that was there. It turns out the bigger this mass was, if we made this mass bigger and bigger and bigger and bigger and bigger, this made this block more likely to move. So we know that friction opposes the motion of an object, but friction can be overcome and made to move in a particular direction. Friction occurs because every object has what we call surface irregularities. You may think of something as a box as being a perfect box, but when in doubt, there's actually tiny surface imperfections. And it's the interactions of the surface imperfections with whatever the object is and whatever surface it's on that actually cause this friction force. Even very smooth objects have bumps at the microscopic level. Friction is the resistance force. So you're trying to drag this box across, but what happens is it keeps these surface imperfections keep interacting, causing it to require more force than you would generally think of. Now, friction is actually very useful. Okay, you wouldn't be able to accelerate, speed up, slow down, turn, do anything without friction. Friction is absolutely imperative to your everyday life. You also use friction generally for keeping warm. Okay, if you were to take your hands and rub them together, like we see here, okay, then that's an example of using friction to create heat. Any acceleration we talked about, so speeding up, slowing down, that's an example of friction. If you want to take and you want to start a fire, either by rubbing two sticks together or taking a match and dragging it across a box, or even using a lighter where you're taking flint and you're clicking it to allow it to start a fire. All of those are applications of friction. In addition to that, tires are applications of friction. When it rains, you want a certain type of tire. When you're going fast, when you're going slow, if you're going off-road, you need to adjust the frictional values for a given situation. And air resistance is also an application of friction. When you're skydiving, if you spread out like shown here, you'll have a greater friction or a greater air resistance, which means you'll go slower. If you were to turn yourself into an arrow, in other words, kind of like you're diving into the water, your friction will be reduced. There are two types of friction that we're going to talk about, and they are kinetic friction and static friction. Okay, objects that are moving in motion are subject to kinetic friction. Now, kinetic means moving, so anytime you see the term kinetic, you automatically think it's moving. So objects in motion are subjected to kinetic friction, and that's what you see if you take a ball and you roll it along the carpet. What happens is as you roll that ball along the carpet, the ball will come to a stop. So kinetic friction can actually bring an object to a stop. Static friction, on the other hand, is when the object is at rest. Okay? So if this guy's just leaning against the wall, the reason why he's pushing this wall and his feet don't slip out from underneath him is because there's a friction that's holding his feet in place. Static means still or not moving. So whenever you see the term static, that means the object is not in motion. Static friction prevents motion. Kinetic friction is the one that actually opposes motion. So they're two different forces. Now, static friction will always be greater than kinetic friction. And you can think about it in terms of Newton's first law. Objects like to be lazy. They like to stay as they are. So static friction is that hold of the object wanting to stay where it is, whereas kinetic friction kind of goes against Newton's first law. It's trying to slow the object down. So the static friction will always be greater than the kinetic friction. Friction can be calculated using these two formulas. If you notice, these two formulas are the exact same. The only difference is the S and the K. One stands for static and one stands for kinetic. The formulas are absolutely the same other than that. You have this Fs term, which means stands for the frictional force or the static friction. Fk, which is the kinetic friction. They're the same thing. This mu term is a new term. We haven't seen mu before. And what mu is it's called the coefficient of friction. And it's a measurement of how rough the surface is, generally speaking. It's how much friction is going to occur for two given surfaces. Now, mu has no units at all, and it's our first value that we actually run into that has no units. What mu is, it's a ratio between two forces. If I have newtons over here and newtons over here, I can't have a unit and still have those two things be equal. So because of that, this mu term is actually a unitless value. You cannot measure it. Instead, it has to be calculated. It has to be, you have to take a couple of measurements and you actually have to calculate it. And then the normal force is the force that is perpendicular to the surface an object rests on. It's the force that's exerted by the surface. In this example, it says a 1,000 kilogram car moving down the highway requires 500 newtons to maintain a constant velocity of 30 meters per second. Determine the coefficient of friction between the tires and the road. So you were looking for the mu. It's going down the highway. The key to this question says that the car is moving down the highway at constant velocity. Remember, at constant velocity, what that means is that there is no acceleration, and therefore the sum of the forces has to equal 0. So in other words, we know it travels down a flat highway, so we know that the normal force and the gravitational force are going to cancel each other out. But if we were to take a look at it in terms of the applied force and the frictional force, the force applied by the engine and then the frictional force that's caused by the tire and the roads, those two have to be equal as well, and they have to cancel each other out. So that cancels with that, and then this is going to cancel with this. And so now we can say, all right, we can say the key thing for this particular question is the fact that the force applied has to equal the frictional force. So now we look at our given information. We are given that the force supplied to the car by the engine is 500 newtons. We are told that we have a 1,000 kilogram car, and we are told that it is moving at a velocity, a constant velocity of 30 meters per second. So with that information, let's look at what we're trying to find. We are trying to solve for the coefficient of friction. And the principle that's going to be involved here is the coefficient of friction, or just friction. So we look at our formula. Our formula for friction is the force due to friction is equal to the coefficient of friction times the normal force. Now remember, if we go back to our original diagram, we said that these two things are equal. So in our particular case, the normal force is equal to the mass times the gravity. So our formula we're actually going to use is the force of friction is equal to the coefficient of friction times the mass times the gravity. So now we take a look at our information that we have and what we're trying to solve for, and we go ahead and see if it works out. So I'm trying to solve for the coefficient of friction, and that's in the equation, that's good. I'm trying to solve for the mass, or I have the mass, which is good. Gravity is a constant. We know that's 9.8 meters per second squared. So if we had the force of friction, we could solve this problem. But if you look right here, this is the key thing. The force applied is equal to the force of friction, so that goes right there. It turns out that we do have a piece of irrelevant information here. It tells us the velocity, but velocity is nowhere in this equation. So it's actually irrelevant information. We say the irrelevant information is the velocity in this case. So now we can plug in our numbers. We can say, okay, now I have a force of friction of 500. That's equal to the coefficient of friction, which is what we're trying to solve for, times the mass times the gravity, and we can solve. We would say 500 equals the coefficient of friction times 9,800. Divide both sides by 9,800. And then when we divide both sides by 9,800, we get the coefficient of friction is equal to 0.051. Now remember, coefficient of friction is actually unitless. There are no units. This one says you have a 2 kilogram box is pushed along a level surface with 50 newtons of force, resulting in an acceleration of 5 meters per second squared. It says you want to draw a free body diagram with the magnitude of all forces that are exerted on the object. So remember, we're not only looking at Fg, Fn, Fa. More than likely, we're going to have to figure out this FF value as well. Now, it says draw a free body diagram with the magnitude of all forces labeled. So you can't just say FF. You have to say FF is whatever number of newtons as well. You should be able to do this one fairly easy. So you have your dot, which is your object. Fg is downwards. FF is upwards. And FF equals Fg. And you should be able to get this answer relatively easily based on the question. Now, friction can actually be used to hold a block in place. And if you look at it, if we put a block on a ramp, the block doesn't always move down the ramp. Sometimes it moves down the ramp. If you have something kind of pulling it this other way, it can move up the ramp. Sometimes it just stays in place or at rest. So that depends on a couple of things. So friction being one of them, but also this angle of the ramp itself. If you take this and you move it up, it's more likely to move. So if you have a frictionless ramp, if you were to describe what happens to the block on a frictionless ramp such as ice, it has to move this way. Okay? At no point is the object going to just shoot up the ramp all of a sudden. Objects don't go up the ramps, they go down the ramps. So if you're looking at the net force, force has to be in the direction down the ramp. Now, if you look at that, that presents somewhat of a problem in the sense that, okay, you've got a force upward, or excuse me, a force downward, that's the weight, and then you have really no other forces except for the force, the normal force, which is generally up. Now, if you have the normal force up, those two would cancel and you'd have no net force. But instead, if you remember our definition of normal force is the force that acts perpendicular to the surface the object rests on. Now, for a level force, these cancel out. Force goes up, force goes down, those forces cancel out, and you're left with no net force. But if you were to take a look at the normal force on a ramp, they no longer cancel each other out. You have a force that goes downward, but now the force is perpendicular to the surface the object rests on. So when you do that, these two things no longer cancel out. When you subtract them, what you're left with is a small force that's going down and to the left or in the direction of the ramp itself. So there is no external force that makes the object move down the ramp. What the force that's left over is the leftover by the normal force and the gravitational force no longer canceling each other out. This one asks us to determine the acceleration of a 10 kilogram block down the ramp. Now, this is actually beyond the scope of the regular class. If you were to look at this, this is kind of a pre-AP extension or a bonus. So if you want to go ahead and follow
this example, we have a box that is on a ramp, and it says that we have a 30-degree incline right here, and we know it's a frictionless incline. So we want to know what the acceleration of this box is down the ramp. So the first thing we need to do is we need to look at our forces. Remember, the force due to gravity is always exerted directly downwards, and so we can say that's mass times gravity. And then also we know that the normal force is always exerted perpendicular to the surface. So in this case, the normal force actually acts in this direction right here. So if you notice, these two can't cancel out each other out anymore, because whenever you take these vectors and combine them, they no longer cancel out. In fact, there's going to be a leftover force. So what I'm going to do now is I'm going to draw kind of components of the vectors. I'm going to say, what happens if I were to take this thing right here and draw it down into a triangle? And you'll see why in just a second, but just go with me now for you're drawing it into a triangle. So at this point right here, this angle right here is actually the same angle as the angle right there. It's for geometry. I think it's alternate interior angles is the theorem, but it basically says this angle has to be the same as this one. So now we have a situation in which we have a triangle, and we have 30 degrees, and we have mass times gravity, and we want to know what the acceleration it is of this box is down the ramp. So we want to know what A is. So let's take a look at what information we actually have. Okay. We do know that the mass, we do know that the angle that it gives is 30 degrees. We do know that the mass that we have is 10 kilograms. And we do know that the acceleration due to gravity is 9.8 meters per second squared. So what are we trying to find here? We are trying to solve for the acceleration of this box. Now the principle that's involved here is the fact that normal force is perpendicular to the surface, because we're no longer canceling out the normal force with the weight. So the formula that we're going to use, we're going to say, okay, the sum of the forces is equal to mass times acceleration. Okay, so let's take a look at what we've got as far as forces are concerned. We want to look at the irrelevant information, all that kind of stuff. Part of this component right here, okay, the vertical part of this component right here is actually going to be canceled out by the weight. So you're going to have the vertical part is going to be canceled out. But what's left over is this x component right there. That x component that actually makes it move down the ramp. That right there is the only leftover force. So we know they say it's the sum of the forces, but really it's only one force. And remember, we can say, based on this drawing that we have here, if you have a 30-degree angle and you have the hypotenuse is this, you can solve for this side of the triangle using the sine function, because sine is opposite. Sine of an angle is equal to the opposite over the hypotenuse. Well, this right here is the opposite side, so you can say sine of 30 is equal to the opposite side, which is what I'm trying to solve for, divided by the mass times the gravity. Or in other words, you can say the force, the leftover force, is equal to mass times gravity times the sine of the angle. So whenever you take a look at that and you say, okay, well now I've got the sum of the forces right there. The only force that's left over is mg sine theta. Now you can take that expression and you can plug it in here. And what you get is an expression that says mg sine theta equals ma. Well, if you look, you actually have mass on both sides of the equation. So mass actually cancels out, and what you have now is the equation g sine theta. It turns out that mass is irrelevant in this question. It doesn't matter what the mass of the box is, the acceleration of it is going to be the same regardless. So now you can take a look at this and you can say, all right, well now I can plug my numbers in. G sine theta equals A. G is always 9.8. Sine of 30 equals my acceleration. Well, 9.8 times the sine of 30 gives you a value of 4.9. So the acceleration of the box down the incline is 4.9 meters per second squared. This one says draw a free body diagram for the situation below. Remember what the definition of normal force is, and if the object is at rest, this object is obviously not moving, what the normal force and the idea of rest are going to have to meet in this case. You should be able to do this fairly easily. We've drawn it several times. So it says we should have a force going downward, and then a force that is up and to the right, perpendicular to the surface, and we can label those as Fn and Fg, and those values should be the same length. And then it says the box is motionless. Now if you were to look at just these two forces should actually result in a force down the ramp. Now the only reason why it couldn't do that, or that it doesn't do that, is there must be another force that's exerted opposite of that force. Now, the only reason why there could be a force that's going in this direction without somebody pushing it would be the force of friction.